Okay, good evening, everybody. Can you hear me reasonably well through the microphone here? Okay, well, it's a lot nice to see so many familiar faces. Thank you, everyone, for coming out to Insite for the Silicon Valley Deep Learning Group's regular event. I had my jacket. I guess I lost it while I was hooking things up, so I still look like a roadie. But I'm also your MC for the Deep Learning Group, and myself and Sophia Viklund have been organizing this event now for I guess about 2 years, and this is probably our 20th or so event. And many of you have actually been with us through the whole thing, so that's really fantastic. And I want to thank you guys for coming out. We have, as usual, there's a video, so if you miss something or whatever, we'll put it on YouTube for our viewers at home. You can take a look at it. We have about almost 5,000 people in the group now. So for those who come to the group and enjoy it in person, there's also almost 10 times as many people who are enjoying it on the internet. So when you ask questions at the end, which is always a very important part of our tradition, please make it a point to get the microphone and ask the question into the microphone so that on the viewers at home not only hear the answer, but the question that was being answered. Okay, so let me introduce our speaker, and we start by thanking Insite. So Insite is our host for tonight, and it provided this beautiful facility. Do we have a sponsor? Yes. Besides Insite? Okay, well, we have a sponsor announcement as well. Okay, so I will pass the microphone to Sophia, who can tell you about our other sponsor, and then I'll tell you about Insite, and then I'll introduce Emmanuel.
We have a wonderful sponsor that's been with us for 2 years of existence of the group, and Stephen Colby, head of director of IP for Roger Royce Law. Thank you so much. The best intellectual property attorney in town. So guilty, I use it myself, and also they do all kinds of corporate law. And if you have any questions for any type of exotic IP or even simple IP, please talk to Stephen after.
Okay, thank you very much. So that's Steve Colby. He's here from Royce Law. So they're one of our favorite sponsors. Though Insite is joining us soon as a new favorite sponsor. So let me introduce Emmanuel Amazing from Insite. It's almost amazing. I'm told there's no G, but he's more amazing than I am. So he's 9 out of 10 parts amazing. So Emmanuel, why don't we introduce you here, and you're going to tell us about what you've learned over the years in practical advancements in AI, and I guess I'll let you introduce your own talk. So everybody, let's welcome Emmanuel up to the stage.
Hey everyone, can you all hear me? Yeah, people in the back? Good, yeah? Okay, cool. So today, we're gonna be talking about practical machine learning advice. And so the reason that we called it practical machine learning advice is because I think, actually let's start with like a show of hands for most of you. Who currently works in machine learning, like as a machine learning engineer, let's say? All right, so a few people. Who currently works as a data scientist? Few more people. The other people, what is kind of your background? If you could yell it out, like just physics, web development. How many programmers? Like just web development, front end, back end. All right, cool. So a varied crowd. I think when we talk about machine learning, especially when there's people from a variety of backgrounds, like we often have at Insite, it's very easy to just start off on the wrong foot and just get confused about what we're talking about. So most of you that have worked in machine learning or have friends that have worked in machine learning, have dealt with this trope in the past. What is machine learning? When you say to your friends that you work in AI, they bring up Robocop, et cetera, et cetera, et cetera. So that's what your friends think AI is. But I think as a community, we also tend to make similar mistakes. And so for a lot of us that are machine learning engineers or data scientists, sometimes we see things like that on our Facebook feed. So the cool research that, whether that's FAIR at Facebook or whether that's DeepMind do is often kind of maybe blown out of proportion a little bit. And so people will say like, oh, the bots are taking over, and like reinforcement learning is just going to be like the future, and like the next week it's going to just take over everything. Usually that turns out to be much slower than that and much more complicated. And so what we mean by practical AI is AI that can be applied today and that is applied today at companies, in the Bay Area, in New York, and just around the world. And so here's kind of a random pick of 3 companies that we work with, but that I would consider a good example of practical AI. So top left is Tala. They're in a very crowded space, which is a lot of people right now are trying to do chatbots that automate various processes, whether that's HR or whether that's customer support, et cetera, et cetera. So this is a very active space that's working right now. On the top right, is anybody familiar with which company has this value proposition of you basically submit a web form and they buy your house, or they give you a price for your house based on that, and if you accept the price, they'll buy your house. Anybody? So this is a company called Open Door. They're in San Francisco, and they use machine learning and various techniques, ranging from kind of classical machine learning to deep learning heavily to try to decide which prices to basically give their customers. And the bottom is also a very interesting space, especially to, I think, people that are software driven, which is embedded machine learning. So all of the things that are, for example, everything that's IoT related, Internet of Things, or everything that's related to, you have a camera and you want to automatically detect people, self-driving cars, you want to detect stop signs and other cars, and doing that on embedded devices is also a kind of like a critical challenge of AI today, is that on one hand, you have very exciting research being done, by training a model on, for 6 weeks on 100 GPUs, and then you have somebody needs to have a model that works on a Raspberry Pi. So before we go a little further, I just wanted to give a little background, both on myself and on Insite. So I'm a program director for our AI program at Insite, and I'll explain a little more about what our program exactly does and all the programs that we have. But a bit of background, I studied both comp sci and AI research and management, so I'm kind of a little hybrid profile there. And previously I was doing data science, software engineering, and machine learning at Locomotion and Zipcar. So as I was introduced, people mentioned that we're here at Insite, so you're at our offices. Right over there, you can look out, is the rest of our offices where we currently have a session ongoing. So it's a little late, so most people have gone home. But basically, what Insite does as a company is that we match skilled individuals with teams doing really interesting AI, or for our other programs, data engineering, data science, and health data work. We've existed for a while, and so we have partners everywhere. All these companies work with us and many more. And so there's a lot of the big names here, and there's a lot of smaller teams that are just doing kind of like Pilot AI or kind of like Open Door, just doing very interesting AI work. So basically through all of our existence, we get to chat with these teams, and the way these teams interact with the program is that they come in every session. We have 3 sessions a year, and they tell us a little bit about what they're doing for like an hour in-depth Q&A, kind of like what I'm doing here, but with, imagine a team from each of those companies. And so we get to kind of like ask them, okay, so how do you actually deploy these models? How do you actually train these models? And just learn more about what is actually being done as opposed to what we all see published on, The Verge or TechCrunch. We also have a bunch of alumni. We just beat the 1,000 mark, and our alumni are everywhere, and they're also a huge resource for all of the things that I'm going to talk about later. A lot of the resources are alumni that come back and just kind of basically give us feedback on like, hey, this is what's important right now, this is what we're doing at Facebook, this is what we're doing at Square, this is what we're doing at Google, et cetera, et cetera. And finally, I just used this, one of our slides just to show that we're in multiple places in the country. And the reason I mention this is that AI especially, surprisingly enough, is very localized in how it is. So what AI teams are doing in New York compared to what AI teams are doing in Seattle or in the Bay Area is quite different. And so we get to have kind of a view of how this is evolving. And that's kind of interesting. We have, as I said, multiple programs: data science, data engineering, health data, and AI. But I think today, most of you came to learn about the AI side, so I'll dive a little deeper into that. So, a little background about, again, like kind of how our AI program works and where we derived the things that we're about to present. As you know, AI is becoming more and more popular. The graph that you see here, I think a lot of people used to show for data science, say around 4 to 5 years ago, right? So you had the same curve of like, oh, what is a data scientist? And people just kept searching and kept hiring data scientists. We're seeing the exact same thing happening for AI roles now. So that being said, as I mentioned, we decided to start our own AI program. So why did we need a separate program? That kind of starts diving into the practical machine learning advice that I wanted to mention. And we have this little slide here that explains why we think it's different from things that exist before. So I think most people will be familiar with kind of like the traditional data scientist profile. We also have seen throughout our conversations a huge need for data engineers. So that's basically the basis of everything that us lucky AI professionals get to do, is because data engineers have built it for us. So we have a huge program dedicated to that, and that's very focused on software engineering. And kind of at the mix of software engineering and machine learning is AI or machine learning engineer or deep learning engineer, depending on the roles. And so it takes a very, very specific kind of skill set or intersection of skills for these roles. And so what I want to start by talking about is, from talking with all these teams and from talking with all our alumni, just an overview of what we've boiled down as the main skills that are relevant. So for some of you that are currently working in deep learning or in machine learning, I'd love to know if you think that I missed some, or if you think that it's an accurate list. And for some of you that aren't and maybe want to transition, I would definitely recommend these as areas to focus on, because that's what we've seen currently just yield the biggest improvement in terms of people getting the roles that they've been wanting to get. An additional thing, you'll notice that machine learning engineers, actually maybe I'll ask for a show of hand. How many people have a PhD here? Yeah. So I was going to say that half of the people roughly have PhDs, and usually half of the people don't. You're split exactly down the middle. So it works for this audience. But there's really two backgrounds traditionally that I've seen go towards AI, or that we've seen go towards AI. It's people with a heavy research background, and then people with maybe a heavier engineering background. And so for those two kinds of people, it takes a little bit of a different set of skills to do the transitions. So I'll start with the engineers. So one half of the room can listen to this slide, and the other half will listen to the next one. No, but really, after asking a bunch of teams, we've kind of come out with these 4 skills, like the main skills of, if you want to transition to machine learning and you're an engineer, this is what you need to know. So I'll go over them briefly, but feel free to interrupt me, or like if you have questions, or if something is unclear as we dive into maybe things that are a little more technical or precise, raise your hands and just feel free to ask the question, right? So the first one is the obvious one. It's machine learning theory. I think most engineers that start doing machine learning end up going either like on Coursera or in other like MOOCs, or taking like a class at a university just to learn the fundamentals. And really you can't escape it. A lot of people believe that machine learning will one day become kind of like a toolbox or a library you just import and use mindlessly. We're far from that point today. So understanding how models work, what exactly does it mean to like overfit on a training set, what exactly it means to have the bias variance trade-off, which segues nicely into our next point. These kind of things are super important, and are things that are constantly tested on interviews, but also constantly correlate with success on the job. Statistics is the other one, I think. Has any of you worked on things that say like A/B testing or any experimentation of some sort? So a lot of that was is traditionally maybe considered closely to like data science work, but a lot of machine learning ends up being experimentation. And while you deploy machine learning solutions, you end up basically making experiments on your user. And so understanding exactly the validity of your experiment before you just deploy a new solution, because like people are clicking more on the button, is super important. And finally, there's 2 things that I think are always overlooked and are super, super important. The data wrangling side. Let's just make a random experiment. Who said they were a machine learning engineer? Anybody mention? How much of your time would you say you spend dealing with just the data part of it?
Typical project is 60 to 75% data handling, data acquisition, data fixing, data
Yeah, so I'll repeat that for, it was around 60 to 75%. For both the acquisition, both cleaning the data, both pre-processing the data, normalizing the data, extracting features if you have to. It's a huge amount of work which often goes unnoticed and has maybe become a sort of a trope. But the other thing I want to mention is that it's important because obviously if you don't have data, you don't have a model. But if you look at any machine learning paper ever, any advances that we've seen in the last 3, 4, 5, 7 years, more data will always beat a better algorithm. Right? So if you had to choose, you'd always want just way more data, so just somebody that's excellent at actually getting the last squeeze out of your data source, so you can have like as much data as you can, rather than like the fancy new 8 stacks of bi-LSTMs to do some model. And the last one that I think is super important is debugging and tuning models. Oftentimes, it's easy to like grab a data set, especially if somebody's given you a data set, and you just kind of like, fiddle with a few models. Maybe you settle on a convolutional neural network for some image classification. You take a pre-trained network, you change it. Great, you're done. It ends up being that like 90% of the problems end up being that you do that, and then you deploy your model to production, and then it doesn't work. And like, why doesn't it work? What assumptions did you make? What could possibly go wrong? Like, so this is an example of a famous paper from, I believe, last year or 2 years ago by Ian Good about adversarial perturbations, right? You can perturb any image of a panda here, for example, so that it looks like any other class. So if you want to actually do machine learning, you need to understand exactly what's going on here. How do you apply those perturbations? Why do they work? Why would I never believe that this is a dog, but yet this model is 100% sure? Like it's not like it's a little fooled. It's 99.7% sure it's a dog. And so learning how people can use and attack your system if you're going to be deploying any API ever is super important. Now there's a whole other set of skills for people that have this background, that have the theory background, but that want to get up on the engineering. So a lot of, especially for a lot of us, I think we learned a lot from online courses or just courses where you just have so much theory that you need to get through to understand that you only have time to think about these things. And then it's once you're on the job and you actually have to apply that theory, you're like, oh, these are very important. We were talking earlier about software testing. Software usually, engineers will tell you need to write tests. Testing your machine learning algorithms can be much harder, but is also much more important. How many stories have we all heard about machine learning algorithms that were terribly biased, or that were, awful at one particular subclass of the problem? Those new frameworks are deployed every day, and there's new frameworks to probabilistically test your models, and so I'd encourage you to explore all of them, even after you fit a super cool classifier. Next, system design. How do you integrate your models in production? If you have, I guess for this one, a classical example would be, who's familiar with the Netflix recommendation challenge? Okay, so some people. For the majority that hasn't heard of it, there was a challenge that Netflix threw out about basically building the best recommender system. Think of it, I believe it was a Kaggle competition. If it wasn't, it was very similar. And the metric was how well can you recommend items to users. It turns out that the prize was $1 million, by the way, which is kind of crazy, or prize money. The winning solution was never implemented, ever. Like Netflix just paid out their cash prize and never implemented the solution. Why did they never implement it? Because it was way too complicated. It was too slow to run. It was too hard to train, and it was too hard to maintain. So those are concerns that can seem like an afterthought, but at every company ever that you're going to have to convince of implementing your really cool new classifier, they will ask you to design it so it doesn't break. In the same vein, we're saying 80% is data work. Making your classifier or your model work with any data is half of that work, I would say. Making sure that the input to your models are correct, making sure that the output of your models are correct, making sure that you can take 1,000 requests at once. Let's take the example of OpenDoor again. OpenDoor has to run models to predict the price of your house, and then they buy it. So it's really important that they're not wrong, but also it's really important that if 100,000 people ask for a price right now, their website doesn't just crash. So while they might get a couple percent better by running a very, very heavy, just deep learning model, Maybe they'll start with logistic regression for most cases because that's the important part for them, is that they actually have a business. So making those trade-offs and knowing, when to break out the very complex models and when to stick with a simple SVM or kind of classical machine learning. And the last part, kind of tied to that, is model serving. Anybody that's dealt with, who has ever deployed, say like a web application or something kind of similar that used everybody's like me, that used deep learning, like in the back end to do something? Well, since nobody raised their hands for deep learning, let's say machine learning. So a few people. So what you might notice if you use classical machine learning is for most models, you don't have to really worry about anything. You just kind of like get your data, you run inference, and it's all right. If you try to train any deep learning model or any model that needs pre-trained weights, and we're talking like hundreds of megs of pre-trained weights, or any models that needs a lot of compute, you'll notice that very quickly you're going to have to write a whole bunch of code to make sure that when your model fails, because your server inevitably goes down, then you can reload the model correctly. When your model makes a prediction, you can store that prediction so that you can make your model better. This is like a huge part of the work that I think most of us think is an afterthought, and most companies definitely don't. So that we've seen be kind of a huge just plus sign if people start thinking about that. And in general, I think we all want more like cool deep learning applications to like be in production everywhere. And so in order to make that happen, we all need to make sure that we can actually think not only about the accuracy, but about like how well these are working and how fast these are working and how efficient they are and how easy it is for the person that's going to read my code, after I leave the company to actually change it. So relate to that. Who has done one of these? All right, around half of the people. I would say that most of the people I know that work as machine learning engineers or as data scientists have at least interacted with Kaggle, Coursera, or Udacity during their careers. Whether that's what got them started, a lot of people start off that way before they just go deeper into actually learning these things, or whether that's just something they did on the side as they got education also elsewhere. They're super valuable. Those online classes will teach you key theoretical concepts. They'll provide you with the problem, with the data, and the evaluation metric. I know we were talking about how hard it is to get the data. What's great when you do a Kaggle competition or you take a Coursera class is that they're like, here, have this data, fit it to this, and you can focus on the actual model building part, which is what you came to learn. They also allow you to quickly explore. The important part about that is you can just take a Coursera class and you don't have to commit. And so that's good because you can learn quickly. Now, you'll notice that why all of these are really important and valuable, I wouldn't say they're sufficient to showcase all of the skills that we just went over. So how do you showcase these skills? And in particular, how do you Is it off?
No, it's on now.
Hi. Okay. All right. Beautiful. I'll just kind of. Yeah. Good point. How do you integrate your results? So just for those 2 points, let's just keep on our example of Open Door, right? What is, if you train a classifier for a startup that tries to buy houses and at the best possible price, what's the relevant metric? What are you trying to optimize? Are you just trying to optimize for accuracy or just like mean error? How might that bias your model? And how does that bias impact the bottom line? It's something that's important if you think about business decisions, but if you're ever going to deploy in production anything, anywhere, you also want to think about how do the metrics you optimize for bias your classifier? Will your classifier just increasingly bias the data it's been fed with? Those are things that you need to think of if you build a project and that are harder to think of when you're just given a very contained project. And then guaranteeing robustness in the wild and integrating results into a bigger system just takes a little bit more work. And so the approach that we have here at Insite is 4-week-long projects where we give you a lot of mentorship and try to teach you these skills through our alumni network, through the companies coming, through us. What I want to talk about here is the projects themselves, because while we help you a lot with them if you're an Insite fellow, what we've seen is also for just anybody ever, it is the best way to both learn about these skills, know if the job is for you, if you would actually like that job, and just learn about new techniques in general. So in our case, our projects are 4 weeks long. They're self-driven or consulting projects. Consulting projects, we have some of our partner companies that come, and we have a fellow just build a part of their ML infrastructure for 4 weeks. And they're in computer vision, NLP, and anything else. Here's a few example projects. Can you read this? I'll read over these. This is a bit of a busy slide. An example of a consulting project is a fashion classifier. So anybody that's kind of played with images before could tell you that the fashion classifier, you probably use like a convolutional neural network, probably use a pre-trained one, and you retrain it to get to that to a satisfactory level of accuracy on your data. For this project, though, there was a lot of other problems. Like, for example, this is a fashion startup. They have, let's say, like 50 categories of clothing that they want to detect. But then very often, they'll change. They'll add like 6 categories, remove 3. And then maybe they're adding like 4 sizes, removing 2 sizes. So there was like a bunch of additional problems around like building classifiers that not only are good, but can also be tweaked and changed extremely fast. The other thing is, who knows what this is? Like, this is the image of a man wearing a scarf. But like, has anybody ever seen a heat map, something like that, over an image? See a couple people nodding? Yeah. So this is an attention map. This is an example of, when you have a classifier, you can just use, you can use attention, or you can use various mechanisms to try to determine what made your classifier make a prediction. And while this is absolutely not important to get accuracy, because it doesn't really change your results, it's super important to understand what's going on. And in this case, it was very important because while this is a good example of scarf here and being attended to the actual region of the scarf, critical increases in accuracy were actually done by seeing that the classifier was focusing on the background rather than on the person. And that meant that the data was biased. Another project is the one on the bottom left, which is hard segmentation with deep learning. This is a really cool project, and is for anybody trying to do deep learning. I would recommend this initiative. It's called AI Open Networks, and it's headed by François Cholet. And some of our fellows have done work on these. They're open problems where you just have a data set and you need to solve them. Very similar to Kaggle, except a lot of them are inherently solving very important problems for the world. So that's always satisfying. This was an example of adapting a new architecture. So it's a mix of a dense net and a UNet. If you know machine learning, that will speak to you. If you don't, that would take a while to explain. But basically achieving state-of-the-art results. The middle upper project is a really cool example of one of the fellows in our current session trained a character level model to generate fake Yelp reviews. This example is a fake review, and it works extremely well. So I'd be happy to get into like more details of that one a little later, but I think it's a pretty cool project. A very applied project for a consulting company, customer request classification, which is a super useful project and which is something that you should use first classical machine learning for and then deep learning. And finally, the last two are of particular interest to me. I think they're pretty interesting. On the right, so 75% of the text, 75% of like internet traffic roughly is videos, but we can't search through videos easily, right? We search through videos by searching for names, or we search through videos by searching through tags. Using a combination of detection networks and object recognition networks, character recognition networks, one of our fellows in the current session built this really cool pipeline where you can put a video and it'll output all of the text in all of the walls or whiteboards or anything in the video so that you can search through those. And finally, on the bottom right, something that would be helpful for every event, including this one, you can use deep learning to actually upsample audio. And so if you can imagine, you can send downsample audio files like a recording of me right now and have a deep learning model fix it a little later. And that was another project that one of our fellows did based on a paper that had come out 3 weeks before, I believe. So these are all example projects, but a lot of the way that people get there isn't the way that I think most of us initially get to like the end of one of those, or think of tackling these projects. I think when you see this project, like, you know, a lot of you and me included would just be like, all right, I'll just like grab a data set, train like a super complicated classifier, put it on AWS for 2 days, you know, go on vacation, come back, and I'm done. You know, some of you might know it doesn't usually work that way. And so what I want to present is, through our experience doing these projects and getting feedback from companies and from fellows and having our alumni come in, a project workflow, kind of a way to tackle your own machine learning project. And to make it a little more concrete, you know, I decided to talk about something that's very applicable. Instead of, you know, talking about how would you tackle a machine learning project in general, we're going to restrict ourselves to think about text understanding. And by text understanding, what I mean is pretty simple stuff. Again, if you've done machine learning, actually, let's do a show of hands. Who knows what clustering is? Okay, so half, 60. Could you leave your hands up? All right, so around half. Who knows what classification is? All right. Okay, generation is kind of vague. I meant text generation, but I guess that one's pretty self-explanatory. And so why text understanding and why these 3 tasks? These 3 tasks, if you think about it, cover most use cases. And text is the data that we have in terms of accessibility the most of. So, you know, most people have text data at their fingertips. Some companies have it as their whole business model. You know, Twitter or Facebook just have, you know, tons and tons and tons of data. But most companies in the world have at least, you know, customer support requests or product reviews, right? They want to understand how their products are reviewed. So an example, for example, of clustering is you want to group together all of the common sentences in your product reviews. You know, I have 20,000 reviews of my new, you know, I don't know, t-shirt I'm selling on Amazon. What are the most positively mentioned things, and what are the things that people mention negatively? Classification would be an example of, I get a bunch of customer support tickets of people that can't use my product. Which customer support requests should I answer myself? Which customer support requests should I just forward to like a frequently asked questions page because they're just really something that I've written about and I don't need to do it? And maybe some customer requests I can feed to like a bot because they're, you know, a little too complicated for like the frequently asked questions page, but they don't really need my full attention. So how do we do this in practice? I'm going to like approach this both from how chatting with you know, a bunch of various companies I've seen people do it at these companies, and how you can most efficiently do it for any side project that you could pick. All right. Okay, I'm not going to say every. Most modern advances, or most things that people call AI and deep learning today and that are actually applied and that aren't still at the research phase, are what's called supervised learning. By a wide margin, most people do supervised learning because it's much simpler to be true. We all would like to know how to learn from data that isn't labeled, but it's just simply very, very hard. And so this is a tweet from Richard Socher, who has a very, very popular NLP class at Stanford, and is the, I believe his official title is Chief Data Science Officer at Salesforce. And that's his view on it, is rather than just, you know, trying to figure out how you could do unsupervised learning, just get labels. Whether that's, you know, you yourself, you know, grab a bottle of water and just spend 3 hours labeling your data, or whether that's going on Mechanical Turk. And that's what virtually everybody does. So, oh, and I guess one last thing, this is usually easy to do, right? Most problems are like spam classification or customer, as I said, like customer request segmentation, where you can, anything that you can do yourself, you can just label 100 examples and then just start tackling the problem. Now the next question is, how do you represent data? So who has ever worked in terms of doing machine learning or data science, or even like a simple classifier, let's say like a random forest, on top of text to data? 4 people, I think. All right, good. So these slides are useful. This is great. How do you represent data? For most classical machine learning problems, you'll have, you know, a class you can see here. You're trying to guess which kind of iris this is, and a bunch of features. right? So, and all you take is you take a bunch of features, and then you fit a classifier. Usually there's very simple classifiers that can just try to fit a region. So that's what you see here, is they're fitting the blue region for the blue class, and the purple or the pink region for the pink class, and the white region for the white class, and then you just say, all right, if you're in this region, you're in this class. Done. Now recently, we've been pretty excited about images and deep learning. So how do we represent images? So here's an Excel spreadsheet with just color input on like how. Is it better? Okay. Sorry about that. So this is 7. And usually the way we represent images is just an array of pixels, right? Red pixels, green pixels, blue pixels, for example. And then we have convolutional neural networks that just use that to learn from it. But how would you represent text? So the classical way, as I'm sure some of the software engineers in this room know, you represent letters is just, for example, ASCII, which is like you associate each letter with a code or with. Now the problem is that this is a discrete representation, which means that while pixel intensities make sense, right, and you go from like very intense to not intense at all, that has like a meaning, going from like 97 to 99, like that's a difference of 2, and going from like 97 to like 120, that's a difference of 21, 23. Anyways, the problem is those numbers don't really have meanings as compared to the characters, right? Like you can't really associate the meaning of the number to the meaning of the character, and so it's really hard for an algorithm to learn on top of that, because you need to learn just the structure of language and words. And so if you're just giving an algorithm like 100 examples, like 100 tweets, and you're trying to find which tweets are positive and which tweets are negative, like good luck teaching it English in the process, right? It's pretty hard. The last thing is you could imagine that maybe you could like use that to like learn for like one basic word, but it's really hard to represent a whole sentence. So what we need is a way to represent sentences. This is what we've come to. We're trying to classify text. We're trying to classify, for example, reviews, or classify customer requests. And we just need to represent sentences. Does anybody have any idea of how you could do that? Word to vec. OK. So that's a good idea. And actually, I'm going to talk about it a little later. The problem being word to vec. Who knows word to vec? OK. So you know what? I'm going to talk about that a little later. But that's a good idea. Any other ideas? Yeah? LSTMs with what, sorry? Just LSTMs? Yeah. So LSTMs are a variant of recurrent neural networks for people here that might not know. You can use them to deal with text data. Usually they take in an embedding. So whether you pass them characters or words, you already need to find a way to embed those characters or words in a different way than that. But it's a good point. I'll get to that a little later. Cool. All right. So the first most naive thing you can do is actually just called bag of words. And so imagine you just take your sentence and you just count all the words that are in there, right? So you count all the words and then you just put them in a bag. So you lose all sense of order, but you just say, like, if I say like hello, my name is Emmanuel. You just have like hello my one name, etc. So how does that work? You take a sentence and you just count all of the occurrences. So Mary is hungry for apples. As you know, one at Mary, a one at is, etc. And the second sentence has the word is twice. So you have a 2 on the vector, right? And then you just represent it as a vector that way. And so then for each sentence in your vocabulary, or in your data set, sorry, you have like this sort of vector that represents what are the words in the sentence. And you can imagine that, while this isn't perfect by any means, at least it captures, maybe if you want to do spam classification, there's some words that are very indicative that something is spam, right? So your model could learn very easily that if there's a 1, like in this column, that maybe is like, some common word in a spam email, then you just say it's spam and you're done. So the pros of this approach is the setup is really quick. It works very well if some words are important, and it's easy to directly interpret. Like once you have these vectors, and once you train, let's say, like a simple classifier, so logistic regression, then you can just say like, oh, my classifier is doing this decision because of this side of the vector, and this side of the vector is hello, or as goodbye. So I guess it learned to recognize greetings. The cons are, I'll get to the well, I guess, okay, the fixed vocabulary size. Since you have a fixed vector, you need to know all of the words that you're going to encounter ahead of time. That's a big problem, because if in your training data set you have 10,000 different words, and then you want your algorithm, we're getting back to like deployment problems, right? Like you want your algorithm to work on any set of data, then any sentence that has different words, your best bet is just going to be to ignore these words, which is obviously like a pretty bad bet and can cause a lot of confusion. It also doesn't capture the semantic meaning of words, right? So if you go back to here, the problem is, you know, Mary and John, they're very similar words, right? They're names of people. We should understand that if a sentence says Mary is sick, and if a sentence says John is sick, those sentences are similar, right? But with this, like, we won't really understand that. And imagine even worse, if all of the words are synonym, right? Mary is ill, John was sick, are a little different, but still very similar. Our model will think they're completely different. So that's a huge con. And it does not conserve order. So you want to try to like keep the order of your variables. That being said, usually you get pretty good embeddings. So this is a graph of something that's called PCA, which is very useful to judge your embeddings, and just showing that different classes actually end up at different locations. So you want to try to see how separated the colors are. So it's usually, the reason I mention it is it's usually the fastest thing you can try, and it's extremely good. And I've heard countless amount of people just use it to start. Like I was chatting with Chris Lizivsky at Dropbox, and literally in their like model that they put in production for their OCR, like in Dropbox you can take a picture of a document and just recognize the characters. They're using mostly that to embed the words. But we want to be able to capture more semantic information. So, word vectors. So word vectors basically solve the problem of semantics. You're trying to have similar embeddings, like similar data representation for words that are similar. That would make sense, right? So if you were to classify, you know, some motivational posters, you would want all these words to probably be kind of similar. And word vectors are kind of impressive. Has anybody seen this graph before? A couple people? So these are word vectors. You go from one word to just a vector, and once you have these vectors, you just represent them in space. And what ends up happening is that all of the vectors that are like close to, say, gender, or all of the vectors that are close to numbers, or are close to country names, are going to end up at similar places in your vector space. They're going to be close together. So it's going to be very easy to just look at the words and be like, oh, these are very clearly one category of words, these are another category of words. Similarly, the relationship between words is actually kept. So if you do, you know, the classic example is you do women minus man and queen minus king, you end up with a very similar value. And so you've captured like the concept of gender. So I just described kind of like what they are, or I guess how they are once they're done, but maybe I'll just go a little bit about how you build them. So this is about as mathy as we're going to get. So you know, don't panic yet. But basically, word vectors are just things that you train by looking at a huge corpus of data, and for every sentence, you take a word and you try to predict the context within where that word was found, right? So the cat sits on the mat, you have the mat, and you're trying to predict, oh, it was the cat sits on the, or vice versa. You can do it both ways. So you could take like the cat on the mat and guess sits, or the cat sits on and guess the. And if you do that over enough words, in the case of the very popular Google Word to Vex that's around 1 billion words, you end up just naturally having those semantic embeddings because you naturally learn. Okay. The dog sits on the mat would be very similar, right? A little less similar would be the man. You get to that define sentences. So there's a bunch of them. I believe you mentioned name. It's definitely the most popular one, and it's I would say the first one that you should use. It was trained on over 2 billion words, where, well, there's multiple data sets, but the one people usually use was trained on over 2 billion words. And it's very useful to just, for any project that you're doing, to just grab it. There's pre-trained versions, and they act just as like a dictionary, right? You give it a word, it gives you a vector, and then you can just do your classification. Glove is a little more elaborate. It actually also uses the frequency of words. So if word2vec doesn't work for you, usually you can try glove. It'll give you around 2 to 5% extra, usually precision, sorry. And Cove is a recent one from Richard Socher's lab at Salesforce, which tries to learn the syntax and include the syntax in the vectors. They're much harder to use because you actually need to do some custom work to get them to work, but they usually, again, improve by like, roughly, they claim, I believe, 2 to 14% in terms of most metrics. And so how does that actually work? It's very similar to what we were doing before. You just need to actually have the pre-trained word vectors. So, you have your 2 sentences, and then for each word, you just have a vector. And then at the end, so you just have, the vector for Mary, the vector for is, the vector for hungry, etc. And at the end, average them all together. And that's your I could, but yeah. All right. Is this everybody hear me? Cool. So then you just average everything, and you get your sentence representation. A little just insider tip is a lot of people will start by kind of trying to weigh words differently, right? You can imagine that Mary is more important than So, how did we do? The pros. Now we capture semantics, right? Words like Mary is healthy and John is healthy, or sentences like Mary is healthy and John is healthy are going to be classified very similarly. We also have a dense representation. So instead of having a bunch of zeros and a bunch of ones, which is very hard for a classifier to learn, we have a bunch of continuous values. We get to cheat because we get to use those vectors that have been trained on 2 billion words. So we get to just leverage that knowledge, like have a language knowledge that we wouldn't have by using previous embeddings. And it's still relatively quick. Compared to before, we just need to look up in a table. So you can imagine you can have a database, and you just look up the words in the database, and you embed it. The cons is that we still don't capture the syntax, right? So we still lose all of the order. And you can imagine that for some sentences, order matters a lot. Judging the embedding quality, this looks pretty nice. It looks pretty separated with those embeddings. One thing you want to do is you want to always judge the quality of your model. So judging the embedding is one way. But one thing that might have escaped some of you is that by going from a vec model, since at the end we just get this vector of like size 300, it's very hard to explain the predictions of our classifier, right? Because we could just say like, oh, it's the first 2 components, but the first 2 components are the average of the whole sentence. And so it's very hard for us to actually explain why our classifier is making the decision it's making. And so that can lead to very, very bad problems. So I want to take a little segue to a recent paper. Who has heard of a paper called Lyme? Nobody? All right, get to teach you something. So Lyme stands for, I believe it's on the slide, locally interpretable model agnostic explanation. It's an amazing tool, and it's starting to get used everywhere. And the idea is you can explain any scandal. And you can classify topics super accurately if you're not careful, because in the end your model is just going to pick up on like the subtle first few characters of every tagline, which has like a code that will give you the exact event. And it's very easy to just make that mistake and forget to remove it, and then you get perfect accuracy and you don't know why. If you use this, then you'll know why. All right, so can we do better? That was mostly for embeddings where most of my knowledge stopped, and so I got lucky enough to, again, asked Richard Socher when he dropped by, and he said, not really. If you start looking at more complex embeddings to just have embeddings for other tasks, you risk simply overfitting. But for some tasks, that's not enough. If you want to translate a sentence, if you want to have a dialogue system, or if you want to have pretty hard classifications, you can't just rely on bag of words or word vector approaches. And that's where your approach comes in, which is recurrent neural networks. Here you have a German sentence that if you wanted to translate, you would need usually a LSTM or an RN. So the way recurrent neural networks work, here's a simple example of a character level recurrent neural networks, is you just input a character and it just outputs the next character for a sequence. It just goes on and on and on. And so this, for example, is fed, this is, and every time it tries to guess the next character. And these models work surprisingly well. One blog post I would recommend is Andrej Karpathy has a blog post called The Unreasonable Effectiveness of Recurrent Neural Networks. It's already a few years old, and it's crazy how after a few epochs you can learn to just output Shakespeare or just output some source code, some Linux source code. If you train them for a bit longer and on a bit more of a narrow data set, you can actually generate text, but generate it with really good quality. This is the end result of a project from one of the fellows in this session about generating custom Yelp reviews. Both of those reviews are just kind of examples of reviews he generated after training on 90 million characters from 5-star restaurant reviews. And what's kind of incredible is that by the end of his project, he did the test of asking a bunch of people to pick the real and the fake one. None of us could. And to try out his model, he posted a couple of things on Yelp, and one of them actually got both marked as useful and also personal thanks from the owner of the restaurant. I guess as a takeaway, you might ask why I'm maybe this section is a little shorter than the other ones. Recurrent neural networks are very useful, and they're useful for classification. They're useful for a very precise subset of tasks. But they will also beat most of the previous implementations on accuracy. The only thing is that they'll beat them by such a small margin that it's really not worth the problem, the difficulties of implementing it in production. And so most companies don't bother and stick with the first few approaches. So recurrent neural networks are great because they keep the semantic meaning and they can learn and adapt their embeddings, but they're slow and they need much more compute. If you had to recap this talk in a slide, this is what you would do, but that would be a bad idea because this slide is not great. Basically, the way that this was intended to be used is as a step-by-step guide of you have a problem with text, this is the order in which you should do these things. A lot of us, I think, just want to try LSTMs, and that's fine if your goal is to try LSTMs, but if your goal is to solve a problem and solve it in an efficient manner, usually you should start these approaches, you should start by using the approaches in this order. So again, what have we learned? We just start with a simple prototype. Always remember to inspect and validate the embeddings. The techniques I used to plot the embeddings were PCA and TSNE, which are two common techniques, and Lyme, which is a recent technique that I recommend, and then keep iterating, while always keeping in mind how complex your model is, how long it's going to take to run inference, how fast it's going to adapt as your data changes, etc. Cool. I'd like to also just thank our alumni community for helping me a bunch for this talk, our program directors at Insite. There's not just me, there's a lot of other ones that helped me. Jeremy sitting in the back helped me a bunch. Our industry partners for just all the expertise that they shared with us. And our service providers. A lot of these projects wouldn't have been possible without Paperspace, who kindly provided us with GPUs in the cloud. Cool.
Well, thank you, Emmanuel. So we, as always, we have a little bit of time for questions, and I'd like to encourage folks to ask anything that interested you during the talk you want a little follow-up on, or maybe just an excuse to pick Emmanuel's brain. So does anyone have any particular questions? Well, so I'll start us off. So here's my question. So my question is, you seem to be kind of a word2vec guy. So how does word2vec behave when you have like homophones, like words like fly, like, you know, time flies like an arrow and fruit flies like a banana?
Struggling with this mic. Is this good? Yeah. Yes, that's a really good question. And that's, if you think about it, so I'll answer in two parts. As you can imagine, it behaves badly, quote unquote, because there's one representation per word. But sometimes for those, or most times for those homonyms, they're used in a very different context. And how do you know that, you know, it's the different meaning of the word, or it's a different word? You know because you know the context. And so usually when you actually try to have a sentence level representation, the other words will help you solve that problem. So that ends up not being a problem very often in practice. If you were to classify individual words, that'd be a big problem, and you want to think about ways to do that. But if you're classifying sentences, usually the rest of the sentence will solve that for you. But that's a good question.
Related to that, within sentiment analysis, there's been an historic problem of voice and sarcasm, as in, unless you can do multi-sentence analysis and combine them, you don't know if I'm saying, that's great, or whether I'm saying, oh, that's great. You just have two words, that's great. You don't know if it's a positive or negative. So how do you disambiguate that? How do you figure out voice?
Yeah, that's a super good question, and a really hard problem that I don't think is completely solved yet. So I'll go with the same answer actually, which is context. For most of word vector models, that is a failure mode. You will very rarely catch that. If you use a recurrent model, you could imagine that a lot of what happens in a recurrent model is that different parts of your hidden state capture different things. And so things have been shown, for example, that if you train a recurrent model and sometimes it goes over, you know, URLs, one of the neurons will know that, oh, we're inside a URL right now. So, you know, we did www. You know, Insite data science, and we need to do like .com. The same thing could be understood because you have a neuron that captures tone. In fact, oftentimes in practice you do. And so if you have, you know, a bunch of negative sentiment in the preceding phrases, then that neuron could help the recurrent neural network to figure out. But back to your question, I think for those first few methods, that would definitely be hard, and I would definitely fall within the example of tricky classification where you might need, you know, a recurrent network. If you could not classify from just the rest of the sentence, or the rest of the sentences.
Another question?
And you may, in fact, not be able to determine that at all. If all you have is that sentence in text, you have no voice tone and no context around it. A human couldn't interpret it, couldn't say one way or another. So in that case, there really isn't information that would enable you to figure that out.
Yeah, that's a really good point. And to that point, Andrew Ng usually says that modern AI is whatever a human can do, like, you know, given 1 to 3 seconds. And so for a general task, if you can't look at a sentence and tell me in a few seconds whether it's sarcasm or not, then I'm not going to be able to build a model that can.
Next question? Oh, well, let me get him and I'll get back to you.
So have you ever tried convolutional neural networks? Because there are some paper report, you know, convolutional neural networks has equal or better result, but it's trained or scoring much faster than LSTMs.
Are you referring to the Kim paper, like 2014 Kim paper?
No, I think it recently, it's last year or like this year from Facebook, I think.
Yeah, there's been a bunch of advances recently. In fact, one of our fellows, after getting some good results on kind of the word-to-vec to logistic regression, we decided to try out using CNNs for classification. They improve upon word-to-vec, and this is practical experience. On benchmark data sets, in fact, they have been proven, and there's papers that came out last month on like sentiment classification and a bunch of other tasks to be better than RNNs. And In fact, CNNs are also, as a segue, taking over things like speech generation and speech recognition, which were traditionally, very recurrent in nature. The answer that I've seen in practice is that CNNs tended to be still outperformed by LSTMs. In practical cases where you don't have an insane amount of data, you still have some data. Why that is, I'm not sure. I could venture a few hypotheses, but while those papers, are very interesting, and CNNs work way better than those simple methods that I explained. In practice, for me, they've worked less than LSTMs, but for other people, they worked better. So I guess maybe I'm implementing them wrong.
It's notable what you didn't say. You said that that a major problem is you'll go to a lot of work to set up a model, to set up a classification system, and then lo and behold, there's a whole bunch of new vocabulary that comes in. You scarcely ever use the word learning, in fact, in your models, and it's almost puzzling why that dropped out.
So just to clarify, is it that you said that there wasn't enough mention of actual machine learning and models that learn and adapt?
I would have expected that in your most successful models, they'd have continuous learning built in them. In that, likewise, in any good, successful career, there's got to be continuous learning. If you just do it once and don't do it again, not a good tactic.
Yeah, gotcha. So continuous learning, which is also called active learning in some communities, is really hard. And usually the approach that most people take for continuous learning, so say, again, let's just keep on well, okay, maybe I'll pick a different example from Open Door. Let's say Uber. Let's say you're Uber and you want to do, the pricing of rides, right? These things, as you said, will evolve over time. When it's Christmas time, the prices aren't the same. When it's 2019, it's not going to be the same prices as, it would be in 2013. In practice, though, the way that these things are implemented usually is you have a model that will take a running average of the last 3 months, and you will fit that model on that. And the reason that you end up doing that most of the time is a problem that's called, has various names, but you could call it catastrophic forgetting. And the idea is, as you've trained a model to be very good at classifying some things, and then you take that trained model and you try to teach it new things, it will begin forgetting at a very, very fast pace the previous things it was trained on. So what that shows us is that those models definitely do not learn the way that we do, because when I learn the piano, I don't forget how to speak English, right? And so that's still an open area of research and a part that's quite tricky still.
Time for 2 more questions. Is a question? Really? This is your chance, right? You can ask your homework questions. You can something you're working on for your employer, your startup.
I might have missed the explanation, but how does Insite work? In other words, where do you recruit your candidates and so on?
Yeah. So to find out more and apply, but in more details, so we have open applications for all of our program. The deadline, I don't think is on that slide, that's my bad. It's October 27th for our next program that will start in January. And the way we work is that we have a lot of the people that apply to each of our programs. There's an interview process, as there would be at other companies, except our process is a little different because we're looking for people that have the potential to be great machine learning engineers or data scientists or data engineers or health data practitioners, but not somebody that could start the job right away. The process is an online application and then an interview over Skype, and then the fellowship lasts for 7 weeks and is completely free. So if you were to join Insite, you would join, stay here for 7 weeks, get to chat with all of the partner companies, build a project kind of similar to the ones that you've seen, and then demo your project at those companies, and eventually, move on with the process with them and join one of those teams. So that's how Insite works at a high level.
Final question? Yes.
I was just wondering if you can tell us a little bit about the Inside health data branch.
Maybe, yeah. So I personally work in the AI branch, but I can speak to the health data branch program. So the health data program focuses on data scientists, especially for companies that are in the health data space. And because usually those companies are looking for people that have some prior experience with that type of data, although that's not always required, or some knowledge of how to deal with clinical data. And so it's very similar to our data science program in terms of the statistical and machine learning skills that you would learn, but the domain knowledge, the domain expertise, and the focus is integrally on companies working with health and clinical data.
Okay, let's thank Emmanuel for giving us a great talk.